came to Udine actually to visit somebody at math department, and I happened to step into the mechanics department, and I didn't know anybody there, so I went to the library. And I went to the library, and it was like a miracle. I saw that every book I ever wanted is there, and there is no books that I would not put in this library. So it was as if città ideale, as you would say. There's some place where somebody with invisible hand collected, which means not only the recent ones, but probably ordered some old editions, and really with understanding and with love. And I asked, where is it? And they said there was a professor here before who collected this library, is no longer here. And that's how first I've heard about Gian Pietro. And the most recent... Yeah, but it's in my memory. Like, I remember, like, seeing this... and the most recent unexpected encounter is when I worked on buckling, and I had to find who has a world record in terms of safe loads for bodies of arbitrary shape, in terms of weak local minimum. And to my surprise, but maybe it shouldn't be surprising, I found that it's Gian Pietro, and I read one of his papers that I haven't seen before, and it was helpful. So in the middle between those two events, we have written 3 papers together, climbed one of the peaks in Dolomites, and visited infinite number of churches. So he affected all 3, my brain, my body, and my heart. So, and I appreciate it. So it's a pleasure to celebrate this truly Renaissance man, who on one side challenges the SBV spaces, and on the other hand designed and built his own house. So that's quite a broad range of talents. So it's a pleasure to be here. So I'll be talking about mechanics of muscles, which is, I would say, practically non-existent field. And we have heard here several talks about mature fields where equations are known and analysis is difficult, and one can apply different sophisticated tools. Now, in the area of muscles, I would say that we are still struggling with putting together a consistent set of equations. So necessarily my talk will be just a collection of attempts in this direction, but nothing is final, and that can be attested by Antonio Di Carlo, who is also put some effort into this field. Okay, so... Sorry? Yeah, but there are expected and there is unexpected things. So randomness in life turns out to be an issue, and that's also an issue in muscles, by the way. All right, so I'll start with a picture that referring to the talk of Gian Pietro about domes yesterday. So we seem to be able to now optimize our structures at this level, but we have also other structures that have been optimized by nature, and some people are claiming that this is a future of engineering, so that we are going to deal with this type of structures. And here we have both solid parts and kind of hard parts and soft parts. Here we only have hard parts. So this is an attempt in this direction to try to understand how the soft parts work here, that occasionally can also be hard. Okay, so the starting point is the basic anatomy. In fact, muscles are just cells, and they are particular simple cells because there is an order there, because other cells are more multifunctional. They can hunt for their own food. They need to move. They need to change shape. They need to divide a lot, while muscle cells are more or less, it's an army, it's a military. So they've been created for one purpose, to generate force, and they hardly change in the course of our life. So in this sense, it's still they are alive, but it may be the simplest object. Now, what we are seeing here is the many levels, many scales. And as you see, there is the thin filament at the micro scale. It's a nanometer. And we see some muscle fibers at a micrometer. And when you see the number of elementary units inside the bigger units, you will see the numbers like 10 to the point of 9. So clearly, this number is less than 10 to 23 that we kind of expect as a prerequisite for continuum description to be adequate. And on the other hand, we cannot deal with all degrees of freedom that are present here, and we would like to have a macroscopic description. And this type of macroscopic descriptions are used, for instance, when people model the heart. They introduce muscle fiber in the heart, and they use phenomenology extracted from what is known about muscles, but they use essentially continuum mechanical model, which they couple with a fluid flow, which is a flow of blood, and they try to close the description. So there is clearly need of macroscopic description of those objects. Now, so as you see here at the scale already of a myofibril, which is a micron, there is some kind of regular arrangement here. So regular in the sense that if you look from the side, it's a lattice. And if you look from along the fiber, it's also lattice. But it's not the same lattice as we have in crystals. So this is from the side. It looks like hexagonal structure. But if we look along, it consists of fibers. So it's not interacting particles. It's interacting fibers. This is one thing. And another thing is that these fibers are not interacting through kind of effective springs or interaction potential. There is something what's called active force generation. So somehow we have to accommodate in our modeling this presence of these active forces on one side, and on the other side we have to take into consideration that the units here are sufficiently small to be seriously affected by the Brownian motion that's present at this level. I seem to be having okay, here we are. I think my computer is okay, so I'll try maybe to yeah, I think it's getting frozen occasionally, and it's probably in the just dying in front of our eyes, and maybe we should put it. No, I cannot move it. No, so I guess I better, maybe I'll use the board and explain some of the ideas, but maybe I'll ask our colleague to restart it in the meantime while I'll continue. Yeah, I apologize. There is, you know, it's a random event. It happens sometimes in the life of a computer, and it's very unfortunate when it happens in the most no, it's frozen. frozen. So would you help me maybe to just repeat what we've done before? Yes, and then I should have put it on the stick, and I'll put it on a stick next time. But in the meantime, yeah, no, I'm so used to it. No, no, you need to force. So, and then we try again. Wait. No, no, I do have. Yeah, unplug the screen maybe. Okay, let's try. Yeah, no, we'll put it on. I hope that it allows us again. So when I need, ask. Okay, so I continue then. So do we have a razor? Yeah. No, it happened once, but it was a different reason. It was I used the incompatible kind of tech entrance into PowerPoint. It's too much trust into Windows world. I've been told about this, but here it's just a failure of hardware. Yeah, I guess I'm kind of cursed. Yeah. Yeah. All right. So there are many levels, and one would like a continuum description. And there are several basic experiments that describe a mechanical response of muscles, and those are used phenomenologically, but with a limited success so far. So one experiment is like this. People take a muscle. I need to put a password. Just a second. There is a muscle like this, so it's cut at a certain length, and it's fixed in what one can call a hard device, and then it's activated. So activated, it means that it means complicated thing, but it's exposed to a fuel. So fuel is arriving. Muscles start to contract, it dissipates energy, and as a result, it generates a certain force. And this force is a function of the length, which its initial length has this shape. So what we've done, we created a muscle of at this length, and then we done the activation, and we reached this level of force. This is the active force generation. Of course, the task is to understand what's exactly happening in this kind of quasi-crystal structure that's responsible for this force generation. Now, another type of experiments that people are doing, they're suddenly stretching it. So they're applying, for instance, you are in this point, and you suddenly apply a displacement. So you can, if this is your length, so I remind you that it's a kind of crystal through which we have a constant flow of energy. So it's not in a static equilibrium. There is a lot of dynamics here inside, and but it's in a steady state. Now we want to perturb this steady state. For instance, we can take a length as a function of time and suddenly shorten it like this. Suddenly shorten it. So how this system would react? Those are experiments were done in the 70s. So it turns out that if you draw here a force, that's usually here denoted by t as a function of time. The force up to this moment was constant. It was this value. Sometimes it's called T naught, so it was this T naught level. Then force suddenly drops because the length diminishes. Then there is a recovery to a certain level, and that recovery happens at the scale of milliseconds. And then there is a much slower recovery all the way up to the level this already happens at the scale of seconds at the original level. So there is something inside our material that allows us to first to recover the force. Remind you that if you just take a spring, the spring would just react elastically and the force would drop. Now, there seem to be two levels of resistance inside this system. So first, it uses one mechanism to recover this force partially at a very short time scales. And then it has another mechanism that recovers force completely at a long time scale. So
you have the initial force even though the length is steadily different.
Sorry?
L
is fixed, yes.
So it's smaller, but you feel the initial one.
Yeah, exactly. So it's shorter, but it recovers. So this is a response that's called T1 in this business, and this is what is called T2. And at the beginning, when people encountered this, so there are basically the two problems I see in muscle mechanics. First is understanding the first plateau, which is a kind of wimpy muscle mechanics. And the second is to understand the second recovery, which is much more serious. Why it's much more serious? Because at this scale, at this time scale, when this force is recovered, it's already comparable in terms of time scale with the delivery of rate of delivery of the fuel. So here, this second stage, which by the way has to be drawn like this, which is much slower, it's a kind of rate limited by the delivery of the fuel, which is you maybe know this. It's called ATP here, the gasoline that's used. It's a kind of final product in our metabolic chain. So this process requires fuel, while people think that this process does not require fuel, and it's last attempt can assure you. Okay, maybe. All right. So I have two parts in my talk. So we have more success in understanding this first part, and at the end there are some preliminary results on understanding this part. Because to understand means to first confirm the micromechanism, and second to come up with the macroscopic behavior. And when this first discovered, people thought, okay, it's just a mechanical machinery, and it must be visco-elasticity of some type. And in fact, it's not a normal visco-elasticity because of the following reasons. So if you plot this T, so if you use notation delta for this shortening, and plot delta here, and here delta, okay, this is the direction of, so here delta is negative. That's how it is usually shown in this world. So delta is negative. And here people plot, this is the value of T naught. So when we shorten, first force drops, and in fact it drops almost linearly. So this is T1 of delta. That's the way it's shown. But then when force recovers, people see behavior like this. While if it were linear viscoelasticity, for instance, it would have been another straight line. So in fact, people see the quite explicit plateau here. And one of the issues is how to explain this plateau and how to think about the mechanism here that would justify this plateau. So why do you need a plateau? Because when you shorten, you recover, okay, it's not exactly a horizontal plateau, it's slightly negative because it produces this T2, and then and this T2, at least at small deltas, constitutes, okay, wonderful, wonderful. It's a miracle. No. I have a slide about this, so okay, so I apologize again. So the main goal is to construct continuum theory with active terms, taking this microstructure into account. And this level, where we have these fibers that interact, there is a thick fibers, thin fibers, and there is these strange appendages. So the interaction happens through these appendages that are constantly in motion. So it's a force that's generated by motion. You may think about that even in crystals, force is generated by motions because there is a quantum mechanics and there is a fields, dynamical fields that's present there. But here it's at the scale much larger than quantum mechanics, and so still we need to understand how it works. Okay, so this is in more detail. When we go to this kind of crystal structure, you see fibers on one side, hexagonal lattice on the other side. At the microscale, this thick filament that's called myosin, thin filament that's called actin, and the appendages that are called cross bridges that are interacting with this fiber. So there is something like this happening underneath. This is a cartoon from one of the books on muscles, but we would like to understand how these guys are actually working. Now, there is, of course, a theory, because people have put a lot of efforts. There are maybe 2 Nobel Prizes that already given in this area. So people tried, maybe even 3 people who contributed to muscle mechanics received Nobel Prize, which is Hill, Huxley, and Katz. So 3 people. So now, but they were all coming from the domain of biology. So they created this type of an image, which is partially based on biochemical reconstructions. So first, those appendages that's here represented schematically as a head and a spring. So this head is doing what is called power stroke. So it changes its angle. So we can view it as a bistable unit, like in our shape memory alloys. So this part we kind of understand. But in addition, occasionally it detaches, because in a detached state it's easier to recharge it, to bring it back from, say, lower minimum to the higher minimum of the energy. And then again it attaches, it does a power stroke. So here people identify 4 basic states: attach, detach, pre-power stroke, post-power stroke, and that's what's called Lymn-Taylor cycle, which is a prominent notion here. In fact, there are many more sites here that people identify, but then they make a chemical theory, because they identify all the states as chemical states, and then the way theories are built, as I realized in biology, they are all of the same type. People write a kind of master equation regulating the jump process between few discrete sites, because in chemistry there are bound sites, and those bound sites have all different affinities. But here there is a speciality of this system, that each site in fact has the spring. So if each site has a spring, in fact it's not a point like in usual chemistry, but it's a manifold. So you have to introduce rates of transition not between the discrete sites, which means you're not using the constants, rate constants, but you're using rate functions. And here we have a huge freedom of inputting phenomenology, because even though some ratios of these constants are constrained by so-called detailed balance conditions, but we still have a freedom of putting functions. And since the first quantitative theories of Huxley, you will find in muscle literature a lot of different strange functions almost drawn by hand. Then when mathematicians come, they study the inverse problem, to what extent you can reconstruct those functions from observations, and they found that it's non-unique. It a little bit reminds plasticity theory, where all kinds of memory dependencies and hardening laws and cross-hardening dependencies were put phenomenologically. And in fact, the problem here is that you put functions rather than constants into the theory. And obviously, when you have a freedom to put a function, you can fit the curve. And many of the curves have been fit, and up to now those theories are being created, and they seem to be successful. But the problem here is that first, we don't have a sites, we have distributed states, we have energy wells, and second, we would like to replace, for instance, attribution of these kinetic rates between the sites by just reconstructing energy landscape in this system. Okay, so this is a kind of state of the art, but this is a picture that I tried to draw, this kind of active force generation. This is experimental, this is a scheme. This is a maximum active force. There is also a passive force that also depends on length. This is like what we know in nonlinear elasticity, but this is another type of beast. So this is one piece of information that is known. Another piece of information is so-called force-velocity curve. In our continuum mechanical language, that would be the dissipative mechanism. But of course, it's not only this. So, for instance, we know that in viscosity, we have a stress, viscous stress versus a rate of strain. It would be a linear function at 0, then maybe nonlinear, away from 0. But at least it would go from this right quadrant to this right upper quadrant to the lower left quadrant. Why? Because that would ensure that our thermodynamical inequalities are satisfied. Now here we encounter the situation where those curves describing the force-velocity relation, which means that we attach certain cargo, a certain force, and we let the muscle contract, and we measure the rate of strain. We see that we have a little corner here that those curves enter. So this is another major observation, the kind of anti-dissipative behavior, and that must be incorporated into the model. Now, here I started to describe those experiments, short and long time response. So when we suddenly shorten the muscle, it reacts at a millisecond time. This is the blow-up of this region. So you recover this T2 level, and then you much more gradually recover the original, the T node level. So this is in a soft device, this is in a hard device. So it's enough for us to understand. As I said, we'll start with the wimpy theory described in this picture, and then we'll say a few words about how you can recover the original force. Now, this is a more detailed, actually, picture from the paper of Huxley, Simmons, 71. And there is a proposition that here we have a mechanical, purely mechanical response. Now, the problem, as I said, that if you look at this T2 curve, this is the T2, and this is T1. So the immediate reaction is elastic, and then there is a partially, seemingly viscoelastic recovery, but there is this plateau here. And let's see what the viscoelasticity would give us. For instance, if you make this type of scheme that would give us this recovery, we see that we can recover partially the force, and we can even choose the constants. But that would always give us that T2 is another linear function here, while in fact here it's more like a plateau. So that wouldn't be enough to recover the force. So the mechanical machinery there must be stronger because it doesn't want any slack. It doesn't want any relaxation. We should almost immediately recover 90% of the force, and then the last 10% more slowly. So this is not something that is going to work. And there is another interesting experiment that is more recent, showing that this rate of recovery, this kind of almost exponential recovery, is very different in a hard device and in a soft device. It's called, in this business, load clamp experiments, or length clamped. Or load clamped would be isometric, they're called, and length clamp isotonic. You see that people reinvent the major notions in every field, and they associate different names. So the rate of recovery is much larger in a hard device than in a soft device. And this is completely missed by these chemo-mechanical models that I described before. So there is a mechanics here behind it. You cannot just use chemical language, and so this is one of the interesting points in this kind of wimpy side of this kind of quasi-mechanical response. So let's see what we can do here. First, people talk about this power stroke. Now, what is the object that we are dealing with? So this is a thick fiber, these appendages that have, of course, three-dimensional structure, but each unit that extends, that is responsible for active force generation, in fact, it's a very complex molecular and with many, many degrees of freedom. So one would want to extract from this many degrees of freedom just few in order to trace them and kind of eliminate the other ones. And what people know is that the power stroke is the sudden change of angle of the part of this one part of this molecule with respect to the other. So the one clear degree of freedom is associated with this conformational change that has a complex structure. It leads to 70-degree rotation. And that suggests that behind each unit here, there is a double well structure. So let's exploit this double well structure, because we've been in the business of a double well energies for a while. And so far, we're assumed that we are at such a short time scale that the myosin is attached to actin. And so all this recovery of the force is due to this power stroke or conformational change. Now, so this is this reconstruction. This is the model. So the model is you have a double well energy, for simplicity biquadratic here, describing your system. And then there is a extended arm, as it's called. And this arm also has an elasticity. So one can put a spring here. So as a result, we have this type of aggregate, which is a double well energy plus a spring, which will be an elementary unit of our more complex construction. So what's interesting about this unit is that not only that the stress-strain relation is non-monotone, but if you look at it with respect to coordinate y, it's a multivalued. So for each value of y, you may have up to 2 different states. So, so we have to deal with the energies that are, or with stress-strain relations that are multivalued, because there are internal degrees of freedom inside our so-called elementary units. So we'll try to build out of this unit something that's a bit more realistic. And what is more realistic? So this is a kind of arrangement that one can expect. The lattice, the piece of the lattice that we are dealing with, so those are the fibers. This is a schematic illustration of these cross bridges. So here they are attached to the thick filament. They are interacting with the thin filament. So we assume that they are all attached. And then we focus on this unit, which seems to be a kind of natural period here. And this unit can be presented in this form. So it's a kind of one elastic fiber, another elastic fiber, and those fibers are connected by those attached cross bridges, but they have this bistable unit here, bistable unit. So here I also added titan, which is a passive elastic structure, but it's not going to play any role in our discussion, because it's seemingly it's being activated at the large extensions that are beyond the most physiologically relevant range. So, so this is an elementary unit, and as you see, it's up to 10 to the 9 units like this in the bigger system that we would like to describe at the continuum level. But each unit itself has many degrees of freedom, because here it's up to 300 units like this. So we'll focus on this unit first and try to describe its dynamics. So let's make it even more schematic. So which means that we'll neglect we'll make those springs, inside springs, to be infinitely rigid, and replace this by a parallel connection. So those are bistable units, like 300 units. So those are minimally necessary elements to describe observation as far as we could tell. There is one lumped elasticity of the fibers that is put here, and this is our model. Still, we have n equal to 300, so we may still hope to do some kind of macroscopic description here. So you can address this at different levels. So this is like a molecular active, no, this is still passive, but this is like a molecular, big molecular in our solid. And we first need to understand this molecular. So we can understand it at the level of 0 temperature, as Enrico would say, and then at the level of finite temperature and equilibrium and in kinetics. So we'll go through all these 3 levels. Now, because of the double, so what is unusual here is that it's not a series connection as we used to have in statistical mechanics. There is a spatial inhomogeneity that can take care of some of the non-convexity, but it's a parallel connection. So it's a real logical description in one point. But still, there are many units. So let's a few slides describing mechanics. So even mechanics is kind of messy. You have many local minima in this system. This is for n equal 3. As a function of stretch, you put different energy levels. So what you see here is that the global minimum is always achieved on pure states when you are either in pre-power stroke or post-power stroke. So this is a response that you expect in a purely mechanical picture. So if you suddenly shorten it, you bias one of the wells, then all the units go into this other well. And if you stretch it, the units go in the other well. So if, for instance, if you manage to be at this point, which is like the T node in our system, you can achieve force recovery. Moreover, you achieve over recovery. So if you shorten it a little bit, force increases dramatically, and if you stretch it a little bit, force drops. So it seemed to be doing something in the right direction, but not exactly. Here I also follow the difference between soft and hard device and try to explain why the barriers in the soft device are harder than in the hard device. It's already seen in mechanical model, but I think since I used a lot of time, this was intended to describe why there is a difference. But at least already at this level, you see that the response in a soft device must be different than in a hard device. Now let's go to finite temperature. So in the finite temperature, as you've heard from the lectures of Enrico, instead of minimizing energy, you need to compute certain integrals. But in fact, the problem is very similar because you compute integrals over huge space, but the integrals are such that because still the number of points is, the number of units is considerable, and that the most contributions to the integrals are brought by the points where the energy achieves its minimum. So in fact, numerical computation of these integrals is almost equivalent to solving variational problems. However, it looks like here we don't have enough n to really be in the minimum, so we cannot replace it by computations of the minima. That we need to deal with the whole landscape. But so why we compute in these integrals? Because there is this beta. Beta is inverse temperature, so those systems are exposed to thermal vibrations, and this is what makes mechanics at this scale different than mechanics at our conventional scale. People use this metaphor. Even to maintain equilibrium in this micro system, you need to constantly do some work. For instance, if you put a book on the table in a macro world, it will stay on this table forever, of course, if you neglect creep and all other relaxational processes. But in this world, since the system is subjected to random fluctuations, it would diffuse, it would jump, and eventually reach the border and drop. So you have to raise it and put it back. So that means that even to maintain equilibrium, you have to do work. So it's a different type of mechanics. There are some traces, because it all depends on how big is the beta. If beta is very large, then it means the temperature is low, and we are close to mechanical description. And it turns out that in muscles, it can be qualified, at least based on our study, as a rather cold system. So we are not far from, we are not in the kind of temperature-dominated states. All right, so this is the task. The energy is known, both in soft and hard device. I'm dropping the soft device side and focusing on the hard device. Now, if you can compute this, here is the computation of these integrals. In fact, with a double parabolic potential, they can be computed explicitly. There are formulas with special functions, but it's explicit. So instead of this kind of black was a global minimum in the original system. So as beta gets lower, which means as temperature increases, the energy becoming more and more convex, and your stress-strain relation becomes more and more shallow here. But it turns out, so this is a hard device, this is a soft device, similar effect, but now it's a stress that is a variable here, and this is a strain. Okay, so it's kind of expected. But what's interesting is that based on the parameters of the muscle, which means temperature and this internal elasticity, we are in the regime where seem to be, we still have a negative slope. So our free energy is still concave, and moreover, it looks like muscle operates exactly in the spinodal region. So it's sitting in the spinodal region here, but this is in the case of the hard device, so we can constrain it. So in this sense, it's stable. In this sense, when we suddenly shorten it, the force is recovered. And when we suddenly lengthen it, the force is dropped as it should be. So one conclusion, that muscle operates in a spinodal state with negative stiffness. But how can it be? Of course, if we put now these elements in series, then we'll have a decomposition in homogeneity. But it turns out that people don't see the inhomogeneity. So that means that there is somewhere, this is a cartoon saying where we are. So this is an isometric contraction. The stiffness here is negative. And it's needed because in elastic response, the force drops in shortening. But then we almost overreact here. Of course, we are losing some force because it's a complex three-dimensional structure. There is inert elements there. But at least this is how the system. So as a metaphor, you would say we are here dealing not with a normal pendulum, but with a pendulum placed upside down, and there is a mechanism there of stabilization that is needed in order to inform uniformity. But at least all our attempts to deal with the data, we of course wanted very much to make it kind of smooth and monotone. But in fact, it's impossible based on the data. So this one conclusion here, that we operate in the unstable regime. So here there is a little illustration of how you can stabilize the system, because we have a source, we have ATP here. So you may think about some kind of delayed actuator here as used in industry to stabilize the unstable point. You would have oscillatory behavior here, and there are some claims that people see oscillatory behavior. But this is a bit speculative at the moment. And of course, this element is antidissipative. So it's a kind of active control. I put here the word fly-by-wire because, as you probably know, the modern aircrafts, they're all unstable. Because if you are, it's already Wright brothers who have actually argued with the French school that was trying to put stable aircrafts. So they were trying to put unstable aircrafts because, of course, stability is a nice thing, but it's difficult to turn, it's difficult to maneuver. So modern fighters are all built in such a way that their design is unstable, and there is active control that stabilizes them. That's called fly-by-wire. So it looks like muscles are also organized this way, because when you have to react very quickly, you cannot be too safe. I'm not even talking about global minimum. You cannot even be in the minimum. You have to be close to the maximum in order to be able to react, and you must have some kind of stabilizing device, as in our launches in the rockets. There are control devices. But this is another story. I won't dwell into it. I want to go back to my original model and look at kinetics. So far we talked about equilibrium. But in fact, you can also look at the kinetics, so which means you deal with the Langevin type language. So this is a potential of your system. You put a thermostat imitating the thermal environment with the temperature T, and the thermostat consists of two elements, random force and the viscous element. So it's a kind of Langevin thermostat. There may be other thermostats. So you would want to be able to deal with this type of a description. And this is one step towards our visco-elasticity. If we want to really understand whether it's a viscoelastic element, we have to do some homogenization in this system. So it can be done either at the level of trajectories in the phase space or at the level of kind of Boltzmann equation for the system, which is a Fokker Plank equation. Okay, so we have our structure, which has all these units. So you have epsilon i's, which are associated with this variable, the strains associated with this variable, and epsilon y, the strain associated with this collective variable. So epsilon y gives us oscillations already at the level of the fiber, of the myosin fiber, and those are oscillations inside the brush, which describes interaction of myosin and actin. So you have to write a system of stochastic differential equations. These are Langevin equations written in terms of the Wiener process here, with two different viscosities and the same temperature. This is in a hard device, this is in a soft device. So this is basically our mathematical model. And here we have, we need to simplify it because there are too many variables in our kind of viscoelastic response, and also there are random terms. So we would like to capitalize on the fact that n is large and try to see if it can be at the macro scale described as viscoelasticity. So the first step is to because this macro variable is associated with the viscosity of the whole fiber. It's eta y, which is much larger than eta. You can, much smaller than eta, which is considered because this is involved conformational change, and this is a pure stretching. So there is a understanding that this relaxation is much faster, and one can try to adiabatically eliminate epsilon y. Those are specific expressions for the drift terms here. So one can look at the limit gamma goes to 0. This is our gamma because we rescale time. And in this case, there are standard methods allowing us to replace the distribution for this fast variable, replace it by equilibrium 1, and then renormalize coefficients in the remaining kind of slowly varying variables. Okay, so that was an easy catch. But then the more challenging thing is to introduce macro description, which means that we would like to go back actually to variable epsilon y. Let me show you the picture what it is. So we would like to somehow minimize out or do something equivalent to this, all the inner variables inside our molecular, and leave only this macro variable and only trace this macro variable. So for this we have to make some representation. Also we can take the advantage that all our units are the same. There is a permutational invariance. So you can replace the probability distribution for the whole system through this ansatz. There is this epsilon y will be macro variable, and this is a conditional probability for inner variable with a given value of this macro variables. So this is our system. So macro variable is a function of a particular function of the micro variables. So you can use the Ito formula here and write equation for this macro variable that has been, it's like a cell variable in homogenization. And then you can integrate over the micro variable and try to get a close description only in terms of the macro variable. But of course you cannot close it, and you have this, you have two terms. First you have your diffusion term for this macro variable, and you have a drift term. So why there is a hope to achieve something here? Because we expect that because it's a macro variable, the diffusion will be much weaker for the macro variable, and in fact it is, maybe I said it too fast. So this is the integration over micro variable. This is the final Fokker Plank equation for the macro variable, and we still have this drift coefficient that requires the knowledge of this solution of the cell problem, which we have eliminated so far. But you see this coefficient h here in diffusion. For our system, it turns out to be of the order of 1 over n. So because epsilon y was chosen as a sum, it turns out from what we've done before that epsilon y, because it could be adiabatically eliminated, it could be computed as the average of the strains in the individual units. So which means that the diffusion will be negligible for this macro variable. That's a good news at large n. But still we have to make, so this is a macro diffusion, but still we have to close the model because we need those conditional probabilities in order to, or solution of the cell problem in order to find this kind of average force generated by these bistable units. And here I should say that we took a kind of easy path. We assumed that the cell problem has an equilibrium, is an equilibrium, which is not justified rigorously. And this is a weak point here so far. But you can assume that this conditional distribution is equilibrium. Here you can compute everything analytically. And you close the problem in this way. So which means that you have this equation where diffusion is negligible, and you compute the drift coefficient based on local equilibrium hypothesis. So you end up, as you will see, the fit is very good because at least we describe equilibrium and we do a little bit of mistake in rates, but it's not bad at all. Now, what are we having at the end? So in terms of our phenological description. So in order to compute stress-strain or stress-strain rate relation, we have to solve a hyperbolic equation, which is a kind of a Boltzmann. So we did not get viscous fluid, but we got a kind of Boltzmann description. But the good news is that here there's no diffusion, so it can be solved by methods of characteristics and replaced by a set of ODEs. And in fact, it turns out that these entries in these ODEs can be used as internal variables. So it is a visco-elasticity at the end. So our stress-strain relation is coupled to a set of internal variables that satisfies ODEs. But it's, of course, it's not dashpots. It's a nonlinear. And in fact, if diffusion is to be taken into consideration, we have to deal in our continuum mechanical description with this PDEs locally, so which means that we have to introduce fibers describing internal phase space. So that means that the original guess of the pioneers in this field, that it's like visco-elasticity in this short-term response, has a meaning, but it's not a conventional visco-elasticity at all. And you see that we kind of able to recover the response of this fast response of these muscles, but we are missing the rates. And it turns out that you can, if it's like in Timoshenko theory. Originally, Timoshenko derived it with a certain constant that can be obtained through his way of reducing 3D to 1D, but then it started being used as an effective model where the constant was matched to experiments. So here it's very easy in this description that we suggest with a set of attached ODEs, constant, not a function, but a constant feed that would allow you to have a perfect description here. Now, this is a response of the stress in the stress strain. This is elastic response. And kinetic response is not exactly equal to equilibrium because it's slow. But we seem to be able to see more or less monotone curve here in soft and hard device. Okay, now I'm already overused my time, so I'll just say a few words about active force generation. So before I was talking about a simple problem, purely mechanical, but still it had these features of the, you still have to do this homogenization in a stochastic system. Now, how one can model active force generation? So we've been dealing with this type of subsystem, which had a spring and a double well energy. And before, it was attached. This is a cartoon imitating the actin filament. So in actin filament, there is some periodic structure because there are preferred attached sites. And it's traditionally represented by periodic potential with some polarity, asymmetry, but otherwise it's periodic. So we have to introduce another variable here. So not only there is a power stroke mechanism, so this machine, so as I said, at a short time scale, this arrow is not moving, it's too slow. So it can at most maybe oscillating here, securing stability here, but in general, it was assumed so far that it's just locked here, while active force recovery was just due to biasing one of the wells. Now, in addition, this point can also be moving along this landscape. So the simplest model would be with two variables now. Now, before I had many cross bridges. Here I have just one cross bridge. But each one, in addition to this epsilon I that was a variable there, which is now x, there is another variable y. So we have a set of equations here. Of course, both variables are exposed to noise. There is this periodic potential, and there is a double well potential that links the two variables. But now the question is how to represent ATP, how to represent this, the fuel, because we have mechanical system. We seem to have understood the nuts and bolts inside. We took care of the temperature presence, but there is this fuel. How to put in mechanical system a fuel? And there is a debate in the world of this system how to put it. But one understanding is that since this ATP is coming from a chemical reaction, and chemical reaction usually transforms a white noise into a correlated noise, so it should be a correlated noise. So that's the minimal assumptions we are making. So what is fuel? And this is where, of course, we are copying the pattern from the theory of Brownian ratchets here. So we are imitating the fuel by the presence of a force correlated component of noise with zero average. So which means that this force doesn't do anything particular, doesn't push us to the left or to the right. It has zero average, but it's correlated versus this entry here that is uncorrelated. So it can be Ornstein-Uhlenbeck process, or here we just take a periodic force. Now, this force can enter in many different places. For instance, in a traditional Brownian ratchet models, people do something with this potential, so which means that this type of correlated noise enters as a product of the force V or as an additive term here. But my interaction with the physiologists convinced me that they think that it's a power stroke that drives the system. So in this sense, what we are doing is we're actually rocking the double well potential, while actin fiber is passive. So you are rocking this active, so you are doing what is called stochastic resonance here. You are trying to find a periodic force that would maximally affect the system, which means you are choosing the time scales that are frequencies that are in resonance with the characteristic times of changing the wells here, but otherwise it's a periodic function. And so as you see here, there is no force that tries, for instance, to move this point along this landscape, either to the left or to the right. So the average over space force that comes from periodic potential is 0. The integral of the derivative of a periodic function is 0 over the period. The external forces, this has 0 average because it's a noise, and the correlated component also has a 0 average. And still, this system leads to the ratchet effect, Brownian ratchet effect, and it actually creates some kind of, in the space of different variables here, some process that we try to link to Lymn-Taylor cycle, which means that it visits different states. But what's important, it produces this anti-dissipative region here in the force-velocity relation. If the amplitude of the force goes to 0, you are going back to just visco-elastic behavior. But if you put this kind of correlated component of the noise, you are getting non-trivial anti-dissipative behavior. So I have a bit more detailed description here, which I would drop in the interest of time, or I can respond. If there is a question, I just say that there is a homework for everybody to develop a theory of homogenization in discrete stochastic system with rugged energy landscape exposed to a colored noise. Thank you very much. I guess